Oh goodness, time to start. Afternoon everyone, and I hope you are looking forward to a week well done, and the weekend is just a heart's beat away, although may it not rain. At a glance, my lecture summary, just what we're going to cover today is we're going to blast through a few more domain and range examples. I'm going to take this off. We're going to, much better. So we're going to blast through a few more domain and range examples, looking at our various functions. Domain is just a fancy way of saying set of all possible x values or otherwise inputs. And the range was again just a slightly more formal way of saying set of all possible y values or outputs. And what we saw yesterday is if you can, draw yourself a graph, get Desmos on your phone, on your iPad, on whatever device you've got at hand. You can always draw a picture to see what's going on and actually do this by inspection, we say, which is again a fancy word for saying by looking, to be able to determine what the domain and the range is. And at the end of this lecture, we'll look at another type of function called a piecewise function, that is defining things bit by bit. They're a bit more sticky, but if you just slow down and take your time, you can work through those very well. Right, so we looked yesterday, and again, these are I will just get, I'll just show you where we are in the notes. Scroll back up. Do we have an extra example? Oh, my extra example's down a few pages. Let me just sit down. So what we're going to do is largely look at exercise 3.6 on your notes. There are 4 examples here. So I'm just going to look at them, but I might pull back as I did yesterday and do a little bit of an extra example just to talk more generally about, start with a slightly easier example before we go to the hard one. So I've just got some extra paper in here, extra electronic paper, and we'll pull right back. Start with it simple to really get a sense of what's going on. So yesterday, this is always a bit thick for me, slightly more refined. And you'll probably, if you were here yesterday or have made some notes, you will have find the domain and range. So I'm just going to, as a nice kickstarter, just remind us of this example that we looked at last time. And of course, this is our plain old parabola or a quadratic function here. And we looked at that and talked about the domain and the range, all possible x values, all possible y values. One little note that I'll add, if you've got the notes in front of you, you could just add, I'll just call it a bit of an aside or an extra note or a bit of a layered extra information. This function, and in fact the next one that we look at, and f of x equals x squared, I think it's minus 9 that we're going to look at. This function is what we call a polynomial. And what we can say, any polynomial has the real numbers. Remember that R that we did with the sort of the fat stalk? Again, if you're writing it on a font, you have these beautiful curly fonts, but when you're writing it just with pen and paper or otherwise, just a couple of straight lines. So the real numbers as its domain. So actually, this is a quick way to answer these. If you can identify that you're dealing with a polynomial, and we'll look at some things that are x squared, the square root of x is not a polynomial, has the real numbers as its domain. So in other words, the set of all input values will have all of these real numbers, continue in both ways forever and ever. So we said very quickly that the domain for this was all the real numbers. That's another way to write it. And our range, a red scribble there, let's talk about the green one. Again, we're looking at all possible output values. Okay, we've got outputs all here. We don't have them down here. Okay, so our range was starting at 0 and including 0. We've got a square brackets, if you like to think of it as sort of a hug, we're including 0 rather than the non-committal round brackets, increasing without bound there. So that's our domain and our range. And again, doing it by drawing the function, sketching the function, any way you can, by memory, by using Desmos, is a great way to look at that. And then have a wee look, all possible y values for our range, all possible x values for our domain. All right, in a similar spirit, the actual example in your notes is just a slight, call it f of x, a slight extension on this. X squared minus 9. And again, we can note that this 2 is a polynomial. So we can sort of know in advance our domain will be the reals. But we'll just slow down a bit and have a look what we're talking about. So we're going to first draw this graph, and we look, right, we've got a quadratic. So we've got a parabola. That's what this bit's telling us. And this bit is telling us shift down 9. So we'll move that down 9, label that negative 9. And proceed as follows. Let's make that a bit bigger. So there's our parabola there, shifted down 9. So our domain, again, we'll do it in red, all the possible x values. So if I go along, all of these x values, if you think of it, will produce a valid here. So my domain, all possible inputs, again, are our reals. Okay, it could be as big or shooting off into negative infinity. Try not to confuse yourself too much with too many lines, but there's our red bit. Got red. And our range, and this time we're looking at all possible outputs. Well, we've got one at 9. Okay, and again, looking over here, all possible outputs. So they start at and include, negative 9, and they shoot up as follows. So there's the domain and the range for that function there, which is indeed polynomial. Right. Let's have a look at another example. Again, we'll start with something simple and then we'll just shift it a bit. And this is not a polynomial. Right, so the first thing we do is draw this. This is the square root of x, so we're going to draw a little picture here. And I'll just draw a little, see if I can draw a light bulb here. So thinking about the square root of x and just looking at the graph here, we have here, as the graph shows, quantities under the square root sign can't be negative. Okay, so that's going to help us think about the domain. But what about 0? 0 is okay, because in fact we can make sense of the square root of 0. It's just 0. That's that wee point there. And the result of taking the square root is will always shoot out a positive number. All right, so we put in. So that gives us something to say about our domain and our range. So our domain, set of all possible inputs, start at 0 and can get as big as we want. So it includes 0, shoots off without bound. And what about our range? This looks like it's sort of, it's getting less big, less quickly, she says, using another crude language. But in fact, it will very slowly, but it will just keep getting bigger and bigger and bigger and bigger. Just think about it. The square root of 9 is 3, the square root of 100 is 10, square root of 1,000,000, etc. I mean, it's slowly but surely getting bigger and bigger and bigger. So actually I should put that in green, right? So the range, in fact, can start off at 0, but also include shoot off as big as you want. So there's the domain and the range from our square root graph. So with that preliminary done, I'm going to jump to B, right? Sorry, I'll jump to D. So we take the square root graph, so we know the shape, we have a general idea of what the domain and the range is for square roots. What happens when we shift the graph? So here we have a square root, we know what they look like, but what does this do? This is a shift to the left of 4. To the left, that's the positive bit there. So in other words, if we were going to sketch it, or if you were to bring it up on Desmos, shifting it to the left 4. Now what do we say for the domain and the range? Yep, brilliant, exactly, yep. So the range will stay the same, you're exactly right. But the domain will shift back, starting at -4. Very nice, yep. There we go along there. And what essentially you want, I'll put a few more words around this, we really want x plus 4 to be greater than or equal to 0. Remember how we said just up here, keep them in the same screen. 0 is okay, all right. I will come back. The quantities under the square root sign can't be negative, i.e. if the quantities under the square root sign, I'll just write that down. The quantities under the square root can't be negative. Putting that in math speak, that means x plus 4 must be greater or equal to 0. Can't be negative means x plus 4 must be greater or equal to 0. Again, you'll probably be absolutely fine just by looking at the graph and doing that. I'm just sort of teasing apart so you really understand what's going on with the graph here. And in other words, that means that x will be greater than or equal to -4. And that's the same thing as saying this bit here. Yep. So again, different ways to say the same thing. All right, that x must be greater or equal to -4 is the same as writing that domain and that closed notation there. Excellent. Let's push our concentration and just look at one more example. 1 over x minus 2. Actually, quick stop your pens, let's just again pull this back, hear the groans, or you can just look at this one. Let's start with the absolute, essentially easy one. So the next step, putting a -2 on the bottom becomes just not a problem at all. And again, I'll just note this is not a polynomial as well. not a string of x to the powers of something that are integers. Right, so what does a hyperbola look like? It's got these asymptotes here and here. So in fact, any value of x except for x equals 0, yeah. Brilliant, so there it is there. And in fact, it's really annoying to write this using mathematical notation. Somebody should think up something better. Any value of x except equals 0 is a perfectly way nice to say it, but this is how you do it in closed form. So any value of x except x equals 0, so notice I'm putting round brackets. It's the union between these two intervals here. So there's the poor, forget about 0 in here, right? So notice I've got the round brackets to say everything but 0. I'm breaking up that interval into two parts. So that's a very formal, symbolic way of capturing the very simple intuitive concept, any single value except for x is equal to 0. And if it was, say, x is equal to 100, you'd split it at 100 and put those round brackets around there. And similarly, for a similar reason, our range is any value but 0 as well. Right, so now we've crunched through a little bit more, something that's symbolically a little more non-trivial than we're used to seeing. Let's then look at the example that's in the notes. So suppose I just shift this hyperbola around. Now again, when I'm drawing this, I can look at any value is okay except the value x is equal to 2, and that's because I cannot have a function that's dividing, that's got a 0 in the denominator. So I can say any value is okay except x is equal to 2. And what that translates to graphically is I'm going to put a vertical asymptote at the line x is equal to 2. That means it doesn't matter what y is, x will be 2. There's our vertical asymptote, and draw my hyperbola as follows. So my domain, any value is okay except x equals 2. Putting those round brackets to mean up until as close as you can possibly get to 2, but absolutely not including. So I break that interval in half. So there's my domain there. But my range is just the same, because I haven't shifted it up or down. So again, that's a bit of a mouthful. It's a bit of a symbolic mashup, but now you can appreciate. And in fact, that's what mathematicians really like to do, be really precise and clear about things. But often the reverse side of that is that the symbols can get a little bit involved in that quest for absolute precision and clarity. So there are domains and ranges. Just again, the mantra for this particular one is all possible values of x is your domain, all possible values of y is your range. And I will leave those there. So there are the 4 examples that we have done now, and there'll be plenty of practice in your labs to be able to find the domain and the range of similar examples. Right, so the reason I just, I did the range along with the domain because I think it makes sense too, but so there are the definitions for you. The set of all possible input values of functions called the domain, likewise for the range. And we've just done all of those. See above, we did domain and range at the same time. There we go. Right, here is an interesting application, and this one gets this one is on the side of a little more complicated in terms of the examples that you might see, but it actually is answers the question, why should I care about the domain and the range of things? And it comes back to the idea that we were saying, actually, we sometimes want to restrict the domain and the range of what values that a function might spit out, because we need it to make physical sense. And often that is because if we're measuring something like time or length or distance, these have to be positive quantities, otherwise it doesn't make sense. So here's a great example, and this is a rectangle. You know, you could couch it in, you know, trying to measure a field in a farm, for instance. But we've got the area of a rectangle is given by the following quadratic function of x. And so clearly there needs to be some bounds on x. It has to be a positive number, right? Because we can't have negative lengths of things. And so not only does x have to be positive, but this is a side, 10 minus x has to be positive as well. So that's going to create a bit of a restriction that we need to restrict the domain to make sense of this particular problem, at least when we're dealing on Earth and not in some weird ontological other parallel universe in which lengths can be negative. So what is the domain of this function? What restrictions, in other words, do we need to place on x? So there's the connection to actually that the domain is an important thing when we're looking at applying mathematics to the real world. So what is the domain of this function of x? Well, the first thing we notice is that these are lengths. So if you like, we can call this the area can be a function of x. Area, this literally means area is a function of length of sides. And as we've all seen in various contexts, what is the area of a rectangle? It's the base times the height. And in this particular case, our base is our x, and we'll call our height of our rectangle to be 10 minus x. So we've got x times 10 minus x. I can actually just move that up a bit. I think I can. Aha! Very nice. All right, in other words, and so that's, you can see that's where we get the quadratic bit from, because if we expand this out, we're getting 10x minus x squared. So there's the quadratic function of x. Right, so the area is a function of the length of the sides, or the base and the height, however precise you'd like to be. So what we have seen is that we absolutely need these lengths to be, notes on these, I'm going to pull this out, oops, right, we absolutely need x to be greater or equal, I suppose it was a really boring rectangle, to be greater or equal to 0, but so we're dealing with lengths. But we also need, put that in the wrong place. Never mind. We also need our 10 minus x to be greater or equal to 0 as well. All right. So in other words, x needs to be less than or equal to 10. So we've got, putting these both together, we get x needs to be between 0 and 10. So there's our domain there. Now likewise, when we think about the range, and again, in the more abstract case, we would draw this function. I wonder if we've got enough time. Get Desmos up. Let's see if we can grab it. Oops. There we go. Right. X minus x squared. Right, can we just pull that in a wee bit? Here we go. All right, so what we get, we've seen we've got a parabola, but some things that we might notice about that, and we'll actually, we might factorise this so we can see a little bit more in detail, is that, of course, we have here a negative x squared here, so we know that we've got a reflection, so we're turning it upside down in other ways, and we've got various, you could just do it by pulling in some values. X intercepts when y equals 0, y intercepts when x equals 0, so these y intercepts will be, so we can also write that, of course, as x 10 minus x, as we saw, those two sides, so these y intercepts here will be 0 and 10 here. So that gives us a sense, just looking at that, how you can draw that. You can also complete the square, of course, and to find this point here as follows, which Desmos will nicely spit it out for us, of course. You can use symmetry and plug in the value 5 to find this maximum here. So if we're talking about the range, just take a quick sketch of that. I'll minimise that and we'll come back. Oops. Here. So A is a quadratic. So we have seen that we go between 0 and 10. And by symmetry, this point here is 525. This bit tells us about a reflection. Or you can complete the square. Remember that process you did when you want to factorise quadratics? We have enough time. So in other words, if we want to write it using brackets, or we want to factorise it, into a form that we can immediately sketch it, we can rewrite this as, well, we've got negative, we'll just bring the negative outside, x squared minus 10x. So I'll get x minus 5 squared. Now that minus 5 is going to give us an extra 25. Remember, completing the square will give us an extra positive 25. So we're going to need to take it away. So we get minus 25 here. And now I'm going to deal with this negative sign. So I've got this negative in the first bit, and I'll get plus 25 here. All right, so that's, completing the square. Go back to algebra, remember that. Again, this is a wee bit fiddly, this example, because it's got lots of steps of things that you've been used to be doing. But really, the reason to complete the square and write it in this format is literally so then we can draw it. This means move it up 25. This negative sign means reflect. and this means move to the right by 5. And that's how we get our 5 up here and our 25 in our reflection. So I'll put a little exclamation mark or a little emoji with some sweat coming up, because that step's actually requires a little bit of work. But again, if you have the resources of computational power, electronic brains on hand, just grab Desmos to be able to draw a picture. So our range here, and remember we've got this restricted domain as well, just between 0 and 10, because we just wanted to spit out, we needed our lengths to be positive. So our range will be likewise between, in green, as small as 0, whoops, and no greater than 25. And I suppose you could argue around the edges to say this is a very boring rectangle that has sides 0 and 0, but you know. Right, so that closes our domain and our range discussion. And again, it's useful because sometimes we need to restrict the things we're talking about or trying to model because we need to make sense of them in the real world. So there's our range, the set of all possible outputs. For values between 0 and 10, we'll spit out outputs between 0 and 25. Right. Let's now look at piecewise functions, and we've got 3 examples to look at to kind of cover these in more detail. You've already seen a piecewise function, the lovely absolute value symbol. I'll tell you another one which you might see in your travels. And this is an opportunity for me to pull out some more history of maths, but never mind. There is a mathematician whose mother almost must have known he was going to be some sort of engineering or mathematician expert and called him Heaviside. It just sounds like a, precisely because there's a function named after him. Whoops. This is incredibly useful. Heaviside, if it's not all right. Yes. Oops, come back. This is an incredibly useful piecewise function used in solving differential equations and other things, which effectively will turn something on and then it will stay on indefinitely. So if I've got time along here, for instance, if time is negative, it will be 0 and it will switch it on for some point, it could be 0 or 1 to 1 thereon after. So this Heaviside function is incredibly useful and you'll see it all the time. So piecewise functions are incredibly useful in mathematics and engineering contexts. Again, something that switches on indefinitely. So lots of piecewise functions that we see. But let's look at one that is a little bit more complicated. And again, these are nothing new, it's just a slightly different way of expressing things. And again, there's sort of multiple pieces in all of this, which you just need to be careful that you pull out the right piece that you're looking at. Right, so here's an interesting piecewise function. Again, what have we got for the piecewise functions? There's usually 3 important bits. The function itself, then these massively big parentheses, and you can get good at managing to do these, sort of move your arm around if you want, rotate your wrist to do big parentheses. And then we've got the actual function itself, usually defined. It can be as many times as you want, but at least twice. And then the last bit, we've got an aspect of where that particular characterization of our function is valid for there. So these are the 3 bits that you see with the piecewise function. Again, it's quite a bit of symbolism going on, but very ordered and logical, and just it's a matter of being able to identify the parts that you're interested in. So suppose we are trying to evaluate the function. It all depends where the particular points you're interested in evaluating. So again, just like, and I wonder if I'll just insert the page. So we get a bit of, oh, bother. Down this side. So I've got a bit more room. There we go. What it might be a good idea to do is to draw this. And often where it's good to start is reducing the problem down to one that you already know how to solve. It's always a good technique in maths. So you may not know what the piecewise function looks offhand, but you know what each of the parts look like. So here we've got a quadratic. This will be a parabola, which is shifted down 1. And here we've got a straight line. So if we were just to deconstruct those, let's forget about the restrictions in the domain. F of x equals 2 minus x. All right, so this is a parabola shifted down 1. So if we had no restrictions, that's what it would look like. And likewise, we haven't had a straight line for a while. So remember, straight lines are always in the form y equals mx plus c. Here, I'm just going to rearrange things. We've got negative x plus 2. So my m is my slope, my rise over run, my gradient, whatever you want to call it. And here is my y-intercept, my plus c. So in other words, and I'll come back to getting that in a minute, this is telling me I've got a straight line that goes through positive 2, and it goes 1 across, 1 down, 1 across, 1 down, all right? So this will be 2 as well. Again, you can check that by saying x intercepts when y equals 0, y intercepts when x equals 0. So again, a straight line like that. So if we were to look at these separately, that is what we would get. But what we are doing is effectively saying, just write this down here, bloop, x squared minus 1, and what do we have? 2 minus x. What was it? X is less than 2, and x is greater than equal to 2. What we're effectively saying, let me use this, we're interested in all this particular function for all values such that x is less than 2, all right? So if I put 2 here, x intercepts when y equals 0, this will be going through 1. All right, so all of this bit here. And then x is greater than 2 for this one here, so we're interested in all of this bit of the graph here. So essentially when we're graphing that, we're just going to put those two bits together as follows. I will do a sketch, but since we've got Desmos open, let's see if we can get this piecewise stuff to work. So what we do is we first define our restriction. Where is my little keyboard? Here we go. It was strictly less than 2, wasn't it? And then you put the semicolon here with Desmos. And what did we have? X squared minus 1. There we go. So that's for that little bit there in that bracket. And then the next piecewise bit, there might be a more elegant way to do it. If you figure it out, come and tell me. We had greater than equal to 2. Use my semicolon. 2 minus x, wasn't it? So there we go there. You can see both of those bits there, part of a parabola up into 2, and then we hitch on with that straight line. What's really nice to notice here that Desmos does really nicely, see that filled in little dot there? we get all the way to 2, but it's ever so close, but not at 2. So there's, in essence, a little wee circle dot there to mean it's not defined there, but it picks it up underneath there with this closed dot at 2, 0. So that's a very pretty description of how that looks, but again, you can try sketching that on the page. Use some colours if you've got them. You can sort of, there you can see that there. Our parabola x squared minus 1 and our straight line there starting at 2 and going 1 across, 1 down, 1 across, 1 down, our gradient of -1. Right, let me try and all of that to answer these, but okay, so we've got this parabola, comes down, comes back up, and you might put a little wee circle there just because of this strictly less than, and because this bit has this greater than or equal to, I'm going to do a wee filled dot there and zip it down as though it was 1 across, 1 down, 1 across, 1 down, 1 across, 1 down. So that's what that piecewise function actually looks like if it's graphed. However, with this particular thing for evaluating the functions, for those of you that don't like the visual and like the numbers, you can actually do it just by carefully looking at the bounds themselves. So if you're wanting to find these values, and we'll do them 2 ways. Okay, what is f of 0? Okay, so 0 is meaning this is x, 0 is my x value, all right? So when x is equal to 0, I'm still in my parabola here, so I can set it on the graph, and I'll have -1 here, right? So I can read that off the graph. But the other thing I can do is I can say, okay, where is 0? Is it in this interval? Nope. Thanks for that. Is it less than 2? Yes, it is. 0 is in this interval. And therefore, I will use that part of the piecewise equation, or -1. So you can do it by looking, or you can do it by carefully trying to figure out where in your interval 0 is. Likewise with 2, and again I'll rub this out, although you might have more space. So you ask yourself the question, where is 2? Is it in this interval? No, because we've just got a strictly less than sign. Is it in this interval? Yes, it is. In the 2 minus x part of the function that's been described in a piecewise manner. So we get 2 minus 2, because this is telling us x is equal to 2, or 0. And we can do that by looking at the graph. Okay, we switch along, that was x is 0, here's x is equal to 2, and in fact we find out the y value when x is equal to 2 is 0. And likewise we ask ourselves, where is 4? And we can do that looking on the graph. Here's x is equal to 4, it's about here, alright, so it's in this straight line, not here, it's here. So we will use our 2 minus x part of the function described piecewise, so we get 2 minus 4 is equal to -2, which seems about right for where we guessed from my sketch graph there. So that's how to pull out function values from the piecewise. Again, a wee bit, just keep track of your intervals, and again, draw the graph if you can, but of course if it starts being piecewise defined in many, many bits, it gets a bit more convoluted. Right, we will now look at one more. So the idea is to choose the correct definition of x, of the function based on where the interval is. Right. We will try one more, and then we'll have a go at drawing this. Now, actually, there's a bit of a typo in the notes here, so if you can just grab your pens and put this to be -1. Right, so again, and maybe now with your newfound knowledge, you can just get a little bit ahead of me and see if you can scribble these down, but we ask ourselves, which definition do we use for x is equal to -2? Or in my sort of more blunt way, where is negative 2? Okay, which one is negative 2? Right, where is negative 2? It's not greater or equal to 1. It's not between negative 1 and 1. It's in fact in this interval here. X equals negative 2 falls in this definition. Oops. Of the function described in a piecewise manner. So we will use the x squared. In this case, every time I see x, I replace with negative 2, so I will get 4. And again, I could take a minute and draw the graph. I will in a minute, but let's just do it by just general analysis at the moment. Right, again, I ask myself, let's take the next one, negative 1. Which definition do we use for x is equal to negative 1? Or where is negative 1 fall? Right, negative 1, so it doesn't fall in here because we've got that strictly less than sign, but we've got it here because we've got that greater than or equal to negative 1, so there it is there, so we use that middle definition. So we use the, I'll put it in inverted commas, use that definition of our function, and that will just be negative 1. Likewise, 0, where does 0 fall? 0 falls in here. So we pull out that definition again, so we can just literally write down 0. Again, if you like, you're using the definition of x. And where does 3 fall? For which definition do we use x is equal to 3? 3 falls in here. And this is just equal to a number. So no matter whether it's 3 or 3,000, we will always get negative 1. And what you can do is draw that. You've got some nice graph, you've got a nice graph here again, sorry, just change this to negative 1. It's just a bit more interesting to have a constant as our function here. What I'm going to do, just got a few minutes, is we will quickly whack that up on Desmos so you'll get right. Our first bit was x squared, and that was for x is less than negative 1. Our next bit was, again, if you've got a phone handy and you've got your Desmos app loaded up, we've got x is between negative 1 and 1. Oops, strictly, sorry. Ammo. 1, put in our colon there, and what was it? X. Very simple. And lastly, our third bit, just cheat a little bit in the interest of time. Whoops. My clipboard is empty. Okay. Y is equal to x is greater or equal to 1. And we get negative 1. So that's a bit easier. So you can see we've got a nice parabola, a straight line here with rise over 1 to be x, and then just this constant value here, y is equal to negative 1. So you can zip that down. And one last little bit that you should write down, what is the domain and the range of this? And then I'll leave it for you to figure out. The domain is any number that you want, and my range, maybe we'll look at this in more detail later. Everything but not including. This is a bit harder. Right, lovely to spend the week with you. Have a great weekend. I'll see you on Monday. Stay away from the Rona.
up on that order about things. So yeah, but that's
Send your teacher to philosophy class.
yeah, maybe a little bit.
Just like check over in stage 2 last night. Like she said, what is a straight line? Well, it's just a degenerate circle. You know, you just like squat circle.
Eventually, yeah.
Eventually it's a straight line. So go take that to your
I don't think they'd be too pleased, but I might just. Thank
So
you.
nice question. How's the week been going? Is it okay?
What's that,
Too fast, too slow, go at right pace?
What's that?
The material in class.
I just joined actually.
Oh.
I joined this week. I've gone through weeks 1 and 2. I've done all lab quizzes and stuff. So I'm going to do week 4 this week and finish off. So far it's pretty good, yeah.
Okay. All right. See you next week.
Yeah, thank you.
Alright, I've just got a question.
Yes.
So when we're working out the range for this graph,
Yeah.
why is it non-infinity if it's continue to go?
Because we said the only domain that makes sense is between 0 and 10.
Okay, so it's not going to go below
That's
0 and the y-axis
That's,
from there.
that's
Okay.
right. Because actually, if you think about it in real life, right, as a normal human being, not a condition, you always need to have a positive area, right?
Yeah, yeah. Oh, yeah, okay, yeah.
So that's why we actually started by determining the domain.
Yeah.
And given any domain, like you might have said, oh, for some reason, I don't know, the farmer is, likes the number 5, so one of the sides has to be 5 or something. We might have even said the domain is that, and that could change the range as well.
Okay.
So range, that's why you have to always do domain first.
Okay. Yeah, that makes sense.
Yeah. But you're right, it was just this. The domain would be all the reals, and then of course the range would be everything less than 25.
And when you say real numbers, what does that
So it means
actually
like
mean?
half and a quarter.
And what would be an unreal number?
So we've got like, you know how they do natural numbers and whole numbers?
Yeah.
Zero, and then integers, which is negative numbers, and real. So the natural numbers, just 1, 2, 3, 4, 5, the whole numbers add 0 in. The integers add a negative number in. And the reals add a half.
Okay, yeah.
Everything in between the number line. So that's what we call that real. It's good to actually should clarify that, 'cause it's kind of interesting, right?
Yeah. Alright, thank you.
You're welcome.